Hi everybody, my name's Chris Collison and this is lecture 10 of CHMP 442, Physical Chemistry 2, Quantum Mechanics at RIT, and we are using Donald Macquarie's book, and we're approaching chapter 4, and in that chapter we're going to talk about quantum mechanical postulates and the general principles of quantum mechanics. Now in this first lecture I'm going to go through very briefly all of these quantum mechanical postulates, and there's 5 of them. So I'm going to introduce them to you, provide some simple examples, and then we're going to dive a little deeper into some of these. For example, the postulate associated with Hermitian operators. So we'll take a deeper look at that in a subsequent lecture. So I hope you enjoy, and we'll see you on the other side. So let's start by briefly describing the postulates of quantum mechanics, which we're going to look at in this first section. So number 1, we're going to talk about a postulate associated with well-behaved wave functions. A second postulate is going to be referring to how the operators, the quantum mechanical operators, are linear and Hermitian. Postulate number 3 is going to tell us that any measurements made are only going to yield the eigenvalues that we find that come out of solving the Schrödinger equation. Postulate 4 is associated with average values. We saw that in chapter 3, and so there's going to be some repetition there. And 5, we're going to talk about the wave function evolving in time. So what can we say about these postulates? These are formalized, accepted postulates. This is an accepted framework from the community that allows us to move forward. So that's what these postulates are all about. And when we accept these, it allows us to work with that framework as we go on to talk about more complicated systems. Okay, so let's jump straight into postulate 1. And in these slides, I'm going to put some text up front for you. These are things to remember and learn, and then I'm going to provide some examples. So postulate 1, very briefly, this talks about well-behaved wave functions and the probabilistic interpretation of those wave functions. So let's read this through for a second. The state of the system is completely specified by its wave function, which depends on the coordinates of the particle and on time. So the coordinates are the positions x, y, and z, and also on time. So let's write that down mathematically. So I'm going to call this a capital psi, and again I'm going to denote this as being the complex conjugate, and I'm going to say that capital psi is a function of the vector r. These are the coordinates of the particle, so it represents that there's a vector in here, so it's in x, y, and z, or in spherical coordinates. At some point we'll talk about that later. And also time in here, so that wave function is a function of coordinates and of time. So again, I'm also using here the capital psi. So r is a vector quantity there, and t in here. So the important thing here is that this function has an interpretation associated with probability. So basically, as I write this, effectively the square of that wave function, psi star multiplied by psi, and then that's multiplied by a volume element in here. As I've mentioned before, that gives us the probability that the particle lies in that volume element, dx, dy, dz, at a time t. So that's what that tells us. Therefore, we refer to this as, of course, the probability density. And this is our volume And of course, when we combine these together, we get a probability, which of course is stated down here in the second bullet. So we can move beyond this postulate in the following way. So we're going to turn to this third bullet down here. Because of the probabilistic interpretation of the wave function, we must recognize that only normalizable wave functions are acceptable. So what do we mean there by normalizable wave functions? And also, what do we mean up here if we look at the top? We're talking about these well-behaved wave functions. Well, because of that probabilistic interpretation, there are certain rules associated with the form that that wave function may take. So in this next slide, I'm going to talk about how there are important properties for what we classify as a well-behaved wave function. And these are as follows. So little typographic there. That's what happens when you use a voice to text app on your phone. So let's talk about what these other important properties are for a well-behaved wave function. So a well-behaved wave function must be, so it must be continuous, it must be finite, it must be single valued, and it must be normalizable. So we can illustrate these points by looking at the following functions. So for example, consider e to the minus x, and we're going to specify that this happens from 0 to infinity. And it's important for us to state the range of x values that we're going to take in here. Okay, we've seen that in particular, it looks like a little face, but we care about that in particular because we're also going to specify the boundary conditions, usually in a quantum mechanical system. So what does this function end up looking like? So if we look at this function, again, we're only going up to infinity from 0, and so we know that that wave function is an exponential decay, never actually reaches 0, and it starts at a position of 1 in here. So in other words, with those boundaries in mind, it's continuous, it's finite, we never have an infinite value, for example, it's single valued, and it's also normalizable. So let's now take a look at a second function, and that will be the function where we're actually just going to change the limits in here. So we're going to go e to the minus x, but from minus infinity to plus infinity. And what do we expect there? And why now actually does this particular function stop being an acceptable function? So we've kind of already got in this graph in here, we've already got a plot of the function all the way out to plus infinity. But what happens as we go to minus infinity? What happens, of course, is the number in the exponent becomes positive because we've got a positive number, or we've got a minus times minus infinity. This particular function will keep going up all the way to infinity. So that's going to tend to infinity, and therefore there's a problem here, right? We can cross off this particular bullet because now this function is not acceptable because that function will go to infinity as we approach minus infinity. All right, let's reset. So now let's consider a particular function sine to the minus 1 x, and obviously we're going to have a range that makes sense for this function, so we're going to go from minus 1 to 1, right? So that makes sense because sine values can, the sign of numbers can only go between minus 1 and 1. But so why is this not an acceptable function? Well, it turns out in this particular case that it's multi-valued, right? So if we imagine that, let's just draw a sine function for a moment. It looks something like this, right? So this will illustrate the point that we get the sine of that number ends up being equal to 0 for many positions, for example, at 0, at pi, 2 pi, 3 pi, etc. So we're going to find there's multiple. If we plot this value, or if we plot this function at the point when x is equal to 0, we're going to find that there are multiple values that we could plot. So in fact, this function ends up being multi-valued, so we can cross it out and say it's not appropriate. It's not a well-behaved wave function. Okay, and the last example that we're going to provide is the following function. So we're going to go back to this e to the minus function in here, but we're going to say we're going to take the modulus of that. We're going to take the, so they're always positive values, and the range here is going to be minus infinity to infinity. And what does that function end up looking like? So if we draw that function, what we're going to find is it looks something along the lines of this. We're going to, at this point in here is 1. When x is equal to 0, we get a 1 value, and then this function jumps off in here. So right at this position in here, there's our peace sign, we get a discontinuity. And therefore this function isn't appropriate either. So it's non-continuous in here. It's certainly finite, it's certainly single valued, and it's probably normalizable, but it's not continuous. So that's the reason why this function doesn't work for us. So those are several examples for what we would expect to be a well-behaved wave function. It's pretty much all comes down to the idea that our interpretation of the wave function is that when you square it, we'll get a value between 0 and 1 when we integrate that over the limits of our particular system. And so it all comes down to it being a normalizable function. So that's kind of written down sort of in that fourth spot there as one of the important properties for how we classify a well-behaved wave function. So let's take a look now at postulate 2. And postulate 2 is stated as follows: to every observable in classical mechanics, there corresponds a linear Hermitian operator in quantum mechanics. So I call this the postulate associated with operators, and again we remember these terms linear and Hermitian, and there's an operator for every observable. Where do we find these operators? So in Donald Macquarie's book, it's on page 148. It's at table 4.1. What will we find there? We've talked about this already. There's for example, we can write our own little table in here. So this is the name of the observable. Here's the symbol for the observable, the operator symbol. So this is actually the symbol for the observable. And then we're going to have the operator symbol, which is not always the same. I'll explain why. And then there's the actual operation. So this is sort of your standard operator table. So we might have, for example, position, and the symbol for position might be X, and the operator symbol would probably be X hat. It could be, we tend to capitalize operators, so it could be capital X hat. And the operation in that table is going to be, for position, is to multiply by X. Okay, so there's our operation. Let's have a look at a different, let's go to blue in here for momentum. So the position, the symbol for momentum in a particular direction is going to be P sub X. And then we're going to have, again, it typically would be a capital, but the important thing here is we've got this little caret on top, the hat, and the operation in here is as follows: minus I H bar di by di x. That is one to remember because it's going to pop up all the time, but in principle you can always go and look it up in the operator table. And lastly, let's consider, for example, let's look at total energy. Okay, so total energy. Okay, we talk about the classical symbol for total energy being capital E, but the operator symbol for total energy is always going to be the Hamiltonian operator. So this maybe clears this up a little bit. You'll see this. So there's only one operator symbol that we use for total energy, and that's the Hamiltonian operator, capital H hat. And that operation most of the time is going to include the Laplacian operator. This is the kinetic energy term in here on the left hand side. Sorry, that doesn't look so good. That is an inverted delta. So that's del squared, okay, plus now the potential energy, and that's in terms of its position, of the body's position. So there's our operation for total energy. So there's some examples. Become familiar with your operator tables, and that's postulate 2. So again, we remember that these postulates are formalized statements that provide us with a framework that we can build upon. So postulate 3 I call the measurements yield eigenvalues postulate, but so we have to find ways in which we can remember these very simply. But postulate 3 in more detail says that in any measurement of the observable associated with that operator A hat, the only values ever observed are going to be the values that are these eigenvalues, right? A sub n, which satisfy the following equation. So that equation is our eigenvalue equation. Here's our operator, and it's operating on our wave function, which we know completely describes the system, and that returns a bunch of measure values that we can obtain, and these are the eigenvalues in here multiplied by that wave function. And by the way, the set of, so there's going to be a range, a whole bunch of different eigenvalues that you can obtain for a population of particles in a system. But that set of eigenvalues, I'm going to kind of put some curly brackets around this for now. So the set of eigenvalues of the operator A hat is called the spectrum of A hat. We've come across that word spectrum before when we actually do spectroscopy. So we measure a spectrum for absorbance of a particular molecule, for example, where each line in that spectrum perhaps represents a transition between an energy of a certain eigenvalue that's represented by a certain eigenvalue. So that sort of ties in, this idea of a spectrum, okay, ties in also with our working knowledge of spectroscopy as a chemist. So that's postulate 3. So we're really starting to rattle through these postulates now. Postulate 4, the way I remember it is this is the one about the average values. So let's formalize the statement that is postulate 4. If a system is in a state described by a normalized wave function, and that normalized wave function is psi, then the average value of the observable corresponding to some operator A hat is given by the following. So here's our symbol for the average value, and that's equal to, we're going to integrate here, for example, over all space. Note that even with a particle in a box, we can consider all space. We just know that the particle's in the box because outside of the box, that's still all space, but we have an infinite potential. So all space kind of covers everything for us. Here's our complex conjugate of the wave function. Here's our operator. Here's our wave function itself. Here's dx. Okay, even better later on. Okay, instead of dx, we can talk about our volume element, d tau. Okay, so we can expand that, but for now, if we're talking about a measurable in one dimension, dx is fine. And we're assuming, of course, here that this is normalized because psi star multiplied by psi integrated over all space with respect to dx will be equal to 1. If we're describing a system in a state with a normalized wave function, then this expression holds. That's postulate 4. And finally, postulate 5, the fifth of 5. And this is going to start sounding like the title for a Friends episode, but this is the one about the time dependence. Okay, so here's the one about time dependence. Let's state formally that postulate. So the wave function of a system evolves in time according to the time-dependent Schrödinger equation. So remember, the wave function is also a function of time. And so we will typically in this course only work with the stationary state wave functions, time-independent wave functions. But nevertheless, postulate 5 tells us that the wave function of the system does evolve in time according to the following equation. So let's write down the time-dependent Schrödinger equation. So it is h hat, and because it's the time-dependent wave function, so the full wave function, I'm going to use the capital psi in this case, and that, going back to postulate number 1, is a function of the coordinates, the position. In this case, let's just use x and the time t, and that is equal to I h bar di psi by di t. Okay, so that's a derivative with respect to time on the right hand side. That's it. There's our time dependent Schrödinger equation. We may see that again in future episodes of this fascinating lecture series, but for now let's leave it as so, and we'll start to dig in a little bit deeper into some of the points that have been brought up with these postulates in the next section.